All right, so the next thing that we're going to be doing in this unit is dividing radicals, which is a little bit more difficult, only because some mathematician decided a long time ago that it was not proper to leave a radical on the bottom of a fraction. And so our whole goal today is to make sure that no matter what happens, we never leave any answer with a radical on the bottom. So maybe that means that we have problems where we could actually divide the radical, so we do that. Or maybe that means we do something in the notes that we're going to call rationalizing the denominator. So maybe we'll do that. So that's kind of the purpose of today, is that we get it so that we never, ever leave a radical in the bottom of a fraction, ever, okay? Because it's not proper, because some mathematician decided that a long time ago. So up here, we've done this before. I'm going to go ahead and write this nth root of a over b. This is kind of the backwards version, but you guys have seen this before, where if you have a radical over a fraction, you can leave it like this, where you have the fraction with the radical over the whole thing, or you can split it so that the radical's on the top and the radical's on the bottom. And you can do that back and forth depending on your purposes. So you can start this way and put them together as one fraction if that would help you simplify the problem. Or if they're together and it helps you to separate them because you see maybe a perfect square on the bottom and you know that maybe the perfect square, perfect cube, you could simplify separately, then maybe it's better for you to split them apart. So you can do it either way. So if we look at the first problem on this notes sheet, this is one where they have split it apart for you to start with, but for us it's actually better if we think of this together. So what we're going to do is we're going to simplify these two pieces separately. We're going to think of the coefficients as one piece, and we're going to think of the radicals as a different piece. So I'm going to think of this as 12 over 2, because that's easy for me to simplify. And then I'm going to put the radical together, so 160 over 5. And I'm going to put the radical together because I know that 160 divides by 5. That's just easy for me to do. And I can see, sorry, I'm trying to, I don't know, maybe focus a little bit more. And I know that 5 on the bottom is not a perfect square. And I remember my whole goal for today is no radicals on the bottom. So 12 divided by 2 is 6. And then 160 divided by 5. 160 divided by 5 is 32. So that's 6 root 32. And then when you get here, you're just going back to our first day of learning, or even back to previous, because we've already done, square roots for a while. You can do a factor tree, or you can simplify using perfect squares. It is up to you. I'll go ahead and simplify this one using perfect squares. So this would be the square root of 16 times the square root of 2. The square root of 16 is 4. So 6 times 4 times the square root of 2 is 24 square root 2. Okay. For number 2, so just like I said before, I think yesterday when I was talking about what numbers you could add or subtract together, what numbers you can multiply, you can only divide radicals if they're the same type of radical, the same type of root. So these are both fourth roots, which means we can put them together. So I'm going to think of this separately. So I'm going to have 36 divided by 9 times, and then I'm going to have a big fourth root, 1,250 divided by 2. So 36 divided by 9 is 4 times the fourth root of whatever that is, 625. And you might remember it, the fourth root of 625, that is a perfect, this is the word I didn't know yesterday, quarter, perfect quart. I don't know. So the fourth root, if you want to do a fourth root on your calculator, you hit the math, but I don't think there is 4 on here. So you would use option number 5, but you have to hit the 4 first. So I'm going to hit clear. I'm going to hit the 4 first, hit the math button, and then option number 5, and it puts the 4 in there for me. So the 4th root of 625, don't worry, I'm sure we'll do that again in the notes, and if not, I'll come back to it. So 4th root of 625 is 5. So this is 4 times 5, which is 20. Okay. So again, well, I might as well do it right now. The way that I hit 4th root is I typed the number 4, and then I hit the math button on my calculator, math button right there, and option number 5. And what it did is it put the 4 in there for me. So that's how you do a 4th root, 5th root, 6th root, etc. Okay. So for this one, I am going to put the square root over the whole thing. X to the 3rd, y to the 9th, x to the 2nd, y to the 5th. Okay, now off to the side, in case you have forgotten how some of these exponents work, x to the 3rd, x to the 2nd, y to the 9th. That was hard. Okay, y to the 5th. So what you can do is you can cancel 1 for 1. So cancel, cancel, and then 1, 2, 3, 4, 5. So this, when you're dividing with exponents, it works like subtraction. So we have 1x left on top. So it's just x. And then y to the 4th left on top. So it's kind of x, y to the 4th left on top, and nothing left on the bottom. So it's like a 1 left on the bottom, so it's like a whole number. Now at this point, we're transitioning over to one of the problems like yesterday. So now I can say, okay, I've got an x, I've got a y to the 4th. It's a square root, so I'm looking at my pairs. I'm going to consider the x to be a leftover. I've got a pair and a pair. So the leftovers go inside the radical, the pairs go in front of the radical. So I've got a pair of y's, that makes y squared in front of the radical. I have x, so y squared with a root inside. Okay, so that one was a little bit tricky. All right. Next one. DJ. I think that one's dinner. Okay, so 28 divided by 4. 3rd root. Negative 16 to the 6th over 2m. Okay, so 28 divided by 4 is 7. I do have the negative. 16 divided by 2 I know is 8. M to the 6th divided by m. I've got 1, 2, 3, 4, 5, 6, 1. So that leaves me 5 m's on top, so m to the 5th. All right. Now for the 8, you might recognize that as a perfect cube. So a reminder is that with our cubes, you can actually cube root a negative number, and I'll prove it to you. This is number 4 on the list after you've hit the math button. The cube root of negative is just negative 2, so that one was okay. So I'm going to go ahead and take that cube root of negative 8. I'll write this on the side. Cube root of negative 8 is just negative 2. That's a perfect cube. I'm going to say this is 7 times negative 2 times the cube m to the 5th. And so this part we do have to simplify. So we've got 1, 2, 3, 4, 5. There's a triple right there, and we have 2 leftovers. So since we have a triple, that's going to go out in the front with the 7 and the 2. So we've got a negative 14 times m This is going to go left over inside cube root m squared because we have m times m. Okay. Now for this one, they did not have them separated, they had them together. 16 is a perfect square, but if you look at the numbers, those are actually divisible. 48 divided by 16 does divide, so I'm just going to divide those. It's always good to check and see if it'll divide. 48 divided by 16 is 3, so this is just the square root of 3. Okay? This one, you can try it, 40 divided by 27, that doesn't divide. So that means this is one where we're going to be setting it. So here, I can recognize the bottom is a perfect cube. The top is not. So on the bottom, I'm just going to split these apart. So I'm going to say cube root of 40 on the top, cube root of 27 on the bottom. I recognize cube root of 27 is just 3. So that means that on the top, I'm going to have to fix that. On the bottom, I have just 3. Okay? So over here, I'm going to take the 40. I'm going to say that's 2 times 20, 2 times 10, 5. And so we have our triple of 2's, and we have a leftover 5. And so that's 2 cube root 5. Now, when we were done, if the 2 and the 3 could be reduced, we would do that. The 5 we can't touch because it's a cube root and there's no other cube root in the problem. But the 2 and the 3 cannot be reduced. And so we're done. Okay, so number 7. Now this one, it might feel like it's like number 3, but it's really not, because you'll notice the top has x's and the bottom has y's. So I'm truly going to think of these as like 2 separate problems, completely separate. So I'm just going to simplify the top. I'm going to simplify the bottom. The nice thing about the bottom is that cube 64 and 64 is a perfect cube, so I'm going to use the cube function on my calculator. So I hit the math button, number 4, double checking, cube root of 64, yep, is 4. Now I just want to check that y to the 6th, I want to make sure that if those are a perfect cube or if they've got some left over, so I'm just going to double check. There's 6 of them, so I've got 1, 2, 3, 4, 5, 6, and I've got a triple, and I've got a triple. And with the variables, if you have no leftovers, that means that nothing would go in the radical, and that means that with your variables, you do have a perfect cube. And the other way you can tell is that 3 goes into 6. So that's the other way you can tell you have a perfect cube. So we have a triple, that's y times y, which makes a y squared with no leftovers, so nothing to go inside the cube, okay? So that means we just have to simplify the top. So for the top 7, if you were to try to do 7, you can't break that down at all. So our cube is definitely going to have a 7 in it. And then for the x's, we've got 1, 2, 3, 4, 5. I'm going to circle our triple. There we go, we got a triple, and then we've got 1, 2 leftovers. So for the triple, I'm going to put an x in the front. And for my leftover, x times x means I've got an x squared inside. And that's my answer. You guys, I already apologize for how long this video is going to take notes for I'm in class, but usually we're talking and like joking back and forth, and it's not this boring, so I apologize. Okay, this one, let's split it apart. So, and with the other ones, we didn't really do it. We didn't try to see if we could simplify those. So let's try it and just see what happens. It's a decimal. I'm just turning it into a fraction. 7/64, nothing happens there. So just showing you that if you had tried to simplify it in your calculator, kind of like the 40/27, nothing there either. Okay, let's try the weighting one. See if anything happens here. Just turning it into a fraction. Nope, nothing happens. Okay, so let's go ahead and split this apart. So the fourth root of 81. Remember, for the fourth root, there's no button on your calculator, so you have to hit the 4 first, then hit the math button, and it's number 5. So fourth root of 81, that is a perfect fourth. Somebody look it up and then text me on Remind and tell me what a perfect fourth is called. It's 3. Okay, so fourth root of 81 is just 3. And then over here, 32, we gotta break this down. 2 times 16, 2 times 8, 2 times 4, 2 times 2. So, scribble these out because I broke them down. Okay, so we have a set of 4 right here. There's our set of 4, there's our leftover 2. So that's with the 32. So we got 2, 4th root, 2. Now with the W, we only have one of those. So that's a leftover. There's no set of 4 there. Again, with the 2 and the 3, if we could reduce that, we would. But we can't. Okay. So those are the ones like that where they specifically gave you either numbers that, it looks like 1 through 5 were examples where you could easily reduce them. 6 through 8 were numbers where you couldn't reduce them to get rid of the denominator, but they had like a perfect cube in the denominator, a perfect square denominator, something like that. So now the examples are going to be problems where they don't get rid of the denominator, we have to fix the denominator. And rationalizing is that word for what we're about to do. It's called rationalizing the denominator. And that's what we're going to do first, okay? So rationalizing the denominator, we get to problems that are more complicated. Those are examples 15 through 20. And I'm going to have you guys do those in a second video. We're going to practice these easier ones first, okay? So this one, here's how we rationalize the denominator. So we've got 3 over 2 square root 5. The problem is simplified already. Like the square root of 5 is just the square root of 5. It's not a perfect square. 3 over 2 is already reduced. There's nothing you can do with this problem aside from just say like, okay, it's done, but it's improper and mathematicians don't like it. So the way that we fix this is we multiply the problem by 1. And remember, 1 can be the number 1, but it can also be any fraction where you have the same number over itself. So 1 could be 3 over 3, 1 could be x over x, 1 could be 7 over 7, 1 could be pi over pi. And so in this case, the one that we're going to multiply by is going to be root 5 over root 5. Okay, so what happens is when we do this, the top is going to become 3 square root 5. Okay, that makes sense. And then the bottom is going to become 2 times the square root of 25, because root 5 times root 5 is root 25. And then what you can see now is the square root of 25 is just 5. So you have 3 square root 5 over 2 times 5. And then you have 3 square root 5 over 10. Okay? So what we did is we multiplied it by 1, And I'll show you on my calculator. So I've got 3 over 2 square root 5. Okay, so you notice it equals that decimal. And then I have 3 over 2 square root 5 times square over square root 5. So I multiplied it by 1, so it still equals the same thing. And then when I'm done, it is 3 square root 5 over 10, and it still equals the same thing. So what I've done is I've changed what the fraction looks like, but I've not changed what it equals. Okay? So that is called rationalizing the denominator. Okay? 5 over root 5. Okay, so we're going to do the same thing again. So this one, number 10, I'm going to split this apart. So root 8, 15. The root 8 on top, if you have, we've simplified. But the root 8 is not the problem. The root 15 is. So what we're going to go ahead and do is let's maybe simplify the root 8 so we're dealing with smaller numbers, and then we can fix the denominator. So 8 is 2 times 4, 2 times 2. So we have a pair of 2. So this is 2 square root 2. So pair of 2's leftover 2's, or root 15. Okay. So now to fix this so that it's proper for the mathematicians who are peculiar about this sort of thing, we're going to multiply. It's not the problem. They don't care about radical numerator, they care about the denominator. So we're going to multiply by root 15 on top and root 15 on bottom. Okay. So on the top, we have 2 in the front, times root 15 is root 30. And then on the bottom, root 15 times root 15, 15 squared, 225, is root 225. Okay. And 30 over root 225 is just 15. Okay. Now, 3, let's double check. 30 is 2, 15 is 3 times 5. So 30 only has a single, so it cannot be reduced. 30 and 15, we cannot reduce those because that's a radical, that's not. 2 over 15 cannot, so this is our final answer. Okay, you guys, this is taking forever, but we're still going. We're going strong. Just imagine if we were in class. I would have said something very funny right now. You all would have laughed. Okay, everybody laugh. Everybody laugh. We're going to pretend that I said something funny. Okay, good. All right, here's the next one. So, okay, so again, we have the top over the bottom. They have split it for us. Root 12 can be simplified, so let's do that. We can simplify that. I've been doing the factor tree on all of those, so let's do a perfect square version, because it's been a minute on this worksheet since we've done that. So we'll say this is root 4 times root 3, which is 2 square root 3. Okay, so we have on the top 3 times 2 square root 3 over 4 square root 7. So that is 3 times 2 is 6. 6 square root 3 over 4 square root 7. Okay, so remember, the square root 3 on the top is not a problem. The square root 7 on the bottom is the problem. That is what the mathematicians do not like. So that is the part that we're going to be fixing. The 6 over 4 I will be simplifying in a little bit. I'm just not worried about it yet. So I'm going to multiply the problem by 1. The 1 that I'm going to multiply it by is root 7 over root 7. So on the top, I've got the 6. Root 3 times root 7 is root 21. On the bottom, I've got the 4. Root 7 times root 7 is root 49. Four times root 49 is just 7. So this is 6 root 21 over 4 times 7 is 28. Now the 21 I'm not worried about because 21 is just 3 times 7. So that is, you know, that's a single and a single. There's no pairs there to be reduced at all. 6 over 28 we can reduce. Each of those is divisible by 2. So 6 divided by 2 is 3. 28 divided by 2 is 14, and that's about all we can do. So 3 root 21 over 14. Now the 21 and the 14 are so tempting to reduce, but you cannot do it because one's in a radical and one is not. Don't do it. Don't reduce those. Okay, next one. All right, so let's go ahead with this one. We can reduce the top. The bottom, there's a few different ways you could do this problem. So some of you might already be saying, oh, Miss Rice, we could kind of put these together, kind of not. So you can kind of think of this if you want. You can kind of work on it all together. 32a to the 5th over 3a, right? Because that's one of the things we could do. And so we could reduce the a's, right, to get it started. So let's go ahead and do that. So we have a to the 5th over a. Oh, I wrote that where you couldn't see it, sorry. So that cancels. So that's a to the 4th. Okay, so that means we have 32a to the 4th on top, and then 3 on bottom, and square root over that whole thing. And so now we can kind of break it back down. I don't know. Did you guys like that? Was it nice to kind of make the bottom a little bit easier to deal with? I don't know. Let's go ahead and fix the top before we do the rationalizing of the denominator. We could have just left it as it was. It doesn't really matter because you're going to end up with the same answer anyway, but who knows. Okay, I'll go ahead and do the perfect square method again since we did the factor tree on the front so many times. So 32 is root 16 root 2, so that is 4 root 2. Then for the a's, I'm going to stick with doing the, like, kind of drawing them out and counting them because I think it's easier. So 4 a's, we got a pair, we got another pair. There's no leftovers. That means that a to the 4th is kind of a perfect square idea. So that means we had 4 root 2. We also had an a times a with no leftovers for the a's. So we have 4 square root 2 on the top. We also have a times a, so we have a squared. Okay, so that's what we've got. And then on the bottom, we've got root 3. Okay, I hope you guys are comfortable with that. Is everybody comfortable with that? Okay, so now we can go ahead and do our rationalizing. We're going to multiply the problem by 1. So the root 2 is not the problem. All the mathematicians are okay with root 2. They are not okay with root 3. So I'm going to go ahead and multiply by root 3 over root 3. Okay, so 4a squared. Root 2 times root 3 is root 6. Root 3 times root 3 is root 9. 4a squared root 6. Root 9 is 3. Root 6 cannot be reduced. That's just 2 times 3. And then 4 over 3 is not a problem. That cannot be reduced either. It is very tempting to reduce the 6 and 3, but you cannot do it because that's a radical and this is not. So don't do it. Just leave it. Don't do it. Okay. Okay. We've got an 8, we've got a 2, we've got a 2. I do like reducing my radicals on the top at least before I get started. Technically, it doesn't matter. If you want to reduce them at the end, you can. But let's go ahead and reduce this. So 8 is root 4 times root 2. That is 2 root 2. So this problem, why did they do this to us? 2 root 2 minus root 2 all over root 2. You guys, how ridiculous looking. Okay, now the only problem in this problem is the root 2 on the bottom, not the ones on the top. Those are fine. Nobody cares about those. It's only this one on the bottom. That's what we don't like. So when we do this problem, this is the one that we're worried about. Alright, so I'm just going to rewrite it right here because we're going to do some distribution. I'm making my voice weird because I am also boring myself with this video. You might be bored, but I am also bored. So we are bored together. Okay. So on the top, we have to distribute this times this one. So the 2 on the front is going to stay. And then root 2 times root 2 is root 4. Minus. And then this one, root 2 times root 2 is root 4. And then this one times this one, root 2 times root 2 is root 4. Wow. Okay. The square root of 4 is 2. So we've got 2 times 2 minus 2 over 2. Okay, so we have 4 minus 2 over 2. 4 minus 2 is 2, so we have 2 over 2, so we have 1. So if your parents want to know the value of 1 today, you can tell them this is the value of 1, in case they were wondering. All that work to equal 1. Wow. Okay. Alright, now for this problem, root 12 on the bottom can be simplified. I am not a fan of simplifying the problems that I'm going to be rationalizing, so I'm not going to worry about simplifying the 12, like rationalize or simplifying it before I rationalize it. I don't like doing that. I'm not a fan. So I'm just going to start off by writing this problem and getting ready to multiply by 1. I could already tell the 2 and the 6 are simplified already, so I'm good to go there. Okay, so let's go ahead and multiply these. Three root 12 times 2 is 24. Ooh, 12 times 6. Anybody? Anybody? 72. 72. Root 12, root 12. Root 144. Okay. I feel like I should have written smaller on this one, maybe. Okay. 24. We'll do a factor tree on this one. 2 times 12. 2 times 6, 2 times 3. Okay, so we have a pair of 2's. A leftover 2, a leftover 3. Okay, and 72, because I'm running out of space, I'll do perfect square method. So 72 is root 36 times root 2, which is 6 root 2. Okay, so let's replace this stuff. So we've got 3 times the square root of 24. The square root of 24 is 2 root 2 times 3 is 6. Okay. Square root of 72 is 6 root 2. Root 144 is 12. Okay. 3 times 2 is 6. 6 root 6 plus 6 root 2 over 12. Okay. Now this is fun. We cannot do anything with the radicals. You'll be tempted, but don't do anything. The 6, the root 6, the root 2 are here to stay. But the 6 and the 6 and the 12, those you might all notice are, I was going to say intervals. Those are all factors of 6, and so they can all be reduced. So I'm going to divide this by 6 and get 1. Divide this by 6 and get 1. Divide this by 6 and get 2. So this answer, you can write 1 root 6, but you don't really need to. You can just write root 6. Root 6 plus root 2 over 2. Oh my gosh, that took forever.